Over the years, both technology and society have seen big changes. Some of these have been positive, like our vastly improved communication. We can now talk, discuss ideas, and share drawings around the world in a matter of a few seconds. Others have been negative, like the loss of transparency. You can often no longer tell how a product works by looking inside it, and you may have doubts about a company's motivations, whether it's fair or whether it's exploitative. And then there are the changes that are just difficult, like the trend towards miniaturization. It means that products become more portable and often cheaper, and yet it makes repair and recycling much harder. And I think of these as being great progressions, great regressions, and great conundra. So now I'm going to talk about repair through the ages. And the most interesting way to do this is with examples. So here I have 4 products which have all been repaired by other people in the past. The first is a mortar and pestle from Zimbabwe. This is probably 50 or 100 years old, maybe older, and it's made either from Msasa or Monondo wood. These trees grow in the Miombo forests of Zimbabwe, forests which turn red and yellow in the spring when the new leaves come out, rather than in the autumn. And before the rainy season, these trees grow long seed pods like beans, which then explode with a loud crack, flinging the seeds far from the trees and allowing the forest to spread. And you can see that this is made out of solid wood. The mortar has come from a log cut from the trunk of a tree, and then the unwanted material has been chopped away using a chisel or an adze. And the pestle has a noticeable curve. This is because it's been made directly from the branch of a tree. The mortar and pestle are used as a simple way to grind nuts and cereals. I have some shelled peanuts here, and I'm going to pour them into the bowl. The heavy wooden pestle is then taken and pounded up and down on the peanuts to crush them into small pieces. If the peanuts are roasted before they're ground with the mortar and pestle, you get an oily paste instead of this rough powder. And the paste can then be taken and ground further on a special stone, like this one, to produce traditional peanut butter. Over the years, the mortar has developed cracks which run along the grain of the wood. But wood is highly repairable, and the thick walls of the mortar make it even better. At some point, a steel band, perhaps from a packaging crate, has been stretched around the top and riveted together to prevent the cracks from growing longer. And the band is supported on 3 wood screws to stop it falling down lower. The cracks have also been filled with sealant to keep the mortar watertight. And here and there are nails which hold the cracks shut. The owner has also given both the mortar and pestle a coat of varnish to keep them looking good. Now it's likely that the person who owned and used the mortar and pestle was acquainted with the person who made it and the person who repaired it. That is, if they weren't all, in fact, the same person. My next example is an old school bell. I got this from Crowthorne in Gauteng, part of the old Transvaal, and I imagine it's about a century old. It's made out of brass with a wooden handle, and the clapper here is the only moving part. The first thing you notice about this bell is how much smaller it is than the previous example, the mortar and pestle. This is made possible by the casting process. Before the advent of casting, if you'd wanted to build a signal instrument, you'd have had to cut down a tree, take a section of the trunk and hollow it out to make a drum. But with casting, you make a mold out of sand, melt the brass, pour it in, and wait for it to solidify in the desired form. And there's no need to cut away and waste the material you don't want, which means you can make more intricate components out of stronger materials. It's likely that this bell was made in the same province where it was used, but it's unlikely that the maker of the bell knew the eventual owner. And this means that there's a separation creeping in. But the bell obviously meant a great deal to the school teacher who rang it to signify the start of every school day. Over the years, it's developed a crack. This is quite common in bells and cymbals which are used vigorously, and the teacher has taken it and had the crack welded up to repair it. And this welded repair is something that would have needed skills and equipment to be brought in from a larger town. The welding set, the gas cylinders containing the oxygen and acetylene, and this creates a dependence on the supply chain. The last thing I notice is that the teacher has painted this brass bell gold. This is a bit odd. Normally, people allow brass to tarnish or polish it to give a high shine, but it works okay here. The paint adheres and it looks decent. And surface coatings have become much more common with the advancement of technology, either to protect the material from rot or corrosion, or to change its appearance. And they pose a challenge in design for repair because they need to be maintained to ensure that protection and to make sure that the product doesn't end up looking scruffy. My third example is a domestic electric heater. This probably dates from around the time of the Second World War, maybe slightly before or slightly after. And it's what we call an electric fire in British English. This is because in that era, most families had a fireplace where they could burn logs or coal. And this is just the right size and shape to sit in front of that fireplace so they can switch the heat on or off instantly. This heater was built by the Durban Falkirk Iron Company, which survives today as Defy Appliances. The heater is built from cast iron, coated with speckled green vitreous enamel. This means that powdered glass containing an inorganic pigment is melted onto the surface of the iron, and it forms a very durable surface coating, provided that it doesn't get chipped. This green looks as vivid as it did when this heater was made 70 or 80 years ago. And I also love its form. The bulbous curves and the taper from bottom to top, they remind me of a jelly mold. And the switch is very satisfying. And I think to myself, does anyone make a heater which is this beguiling today? I don't think they do. It also contains a lot of standardized parts. The screw threads, the plug, the supply voltage is standardized so that it'll remain useful in the future. Even the thickness of the sheet metal and the wire used to build it. And the elements are modular. A module is something that has standard dimensions and a standard function, like a light bulb, so you can replace it easily. You might also see, now that the bottom element is warming up, that the glowing region is narrower here than it is in the top element. That's because at some point, the wire of the top element, the element which is always switched on, has failed, and someone's replaced it, and they haven't stretched the wire in quite the same way, or done it so neatly so that the glow looks wider. And with these elements, they often fail near the end. And actually you can get away with stretching a few coils out, shortening the element slightly, and fixing the element that way. So modules are a great thing in design for repair because of the ease of replacement. But if you can get inside the module and fix the module itself, that's even better. Here, I've taken off the back cover for a better look at the element modules. These are mounted using simple screws, and simple screws are also used for the electrical connections. This means that it's very easy to swap a module. It's also interesting that this ceramic block was made in England, when the heater was built in South Africa. This marks the start of product manufacture becoming more international. You can also see that while this is a heavy heater, weighing 6 or 7 kilograms, it consists of a hollow cast iron shell. This is an early example of optimization. Optimization means that you use less material to build the product, and it has its advantages and disadvantages. It can make a product cheaper and sometimes improve its performance, but it's difficult to know exactly how much material you can safely remove, how far you can push your luck, because you don't always know exactly how the product's going to get used and abused. And in some cases, computer modeling can help, but not always. And over-optimization can lead to parts breaking more easily and being difficult to repair because of the thin walls. And this can have a negative effect on the product lifetime. Lastly, when it comes to replacing the cover, you can see that the screw holes don't line up perfectly. Here, someone has cut the hole larger to make the screw fit. This was common up until the middle of the 20th century because the parts were made by hand. Thankfully, it's now more or less a thing of the past. The parts are much more consistent and completely interchangeable because with computer-controlled manufacturing, the parts are either all right or all wrong. My last example of repair is this. It's a portable Geiger counter. I believe this was used by Union Carbide during the post-war uranium prospecting boom. In fact, it may have been built by Union Carbide especially for the job. At the time, it would have been a very rare and valuable instrument. It comes together with a fitted hardwood case to protect it from damage. The way it works is that here there's a tube filled with a gas at a low pressure, and when a radioactive particle enters through a window at the end, it knocks an electron out of one of the gas molecules. This electron is then accelerated by a high voltage applied between two electrodes which run along the length of the tube. And as it accelerates, it smashes into more gas molecules, knocking out more electrons, which also accelerate, and an avalanche effect ensues. This causes the gas to briefly conduct, creating a pulse of current, which can be countered by the circuitry to give a measure of the radioactivity of a rock. When you're filming, you don't always get things right first time. I must have taken this Geiger counter apart at least 10 times in the course of the filming, and at one point it stopped working. And I started looking inside for the problem, looking at what could have got bumped or pulled. And I found that one of the little metal can germanium transistors has a broken leg. So now I'm going to repair this spontaneously. See if I can get the leg nicely tinned. And I think it's on. So let's see if it works. Got some thorium gas lamp mantles here because I don't live anywhere near radioactive rocks. And the needle's rising. 5 pulses per second. 7.5 pulses per second. So it's fixed. And that's possible because of the way it's built with the discrete components. You can see everything so clearly and get to it. 10 pulses per second. It's also fascinating to look at how other people have repaired this Geiger counter in the past. The first thing I love is this pair of aluminium angles which someone has attached to the front to protect the panel meter and the switches. This is important because things which stick out from a product are very likely to get smashed or broken off. And if we look inside, there's a round metal clip with nothing in it. This would originally have taken a high voltage battery of the type used in valve radios. But as valve radios were replaced by transistor radios, this type of battery became unavailable. And the owner of this Geiger counter has added a completely new voltage regulator circuit to allow the instrument to run off 2 standard 9-volt batteries connected in series. And this voltage regulator uses more modern components, transistors in plastic cases, smaller resistors, and this, an integrated circuit, the only one in the whole device. This is an early example, a 741 operational amplifier made by Signetics of the United States. And the integrated circuit was a remarkable advance. The idea of taking an electronic circuit and miniaturizing it on a single silicon wafer and encapsulating it forever in a package so that it's protected from the atmosphere and from vibration greatly improves its reliability. But the idea of sealing something for life is a difficult question in design for repair. And it's not a new question. There are examples from the early 20th century, like the Warren Telechron synchronous clock movement, which sealed a gear train together with a lubricant in a metal can. And today, clock enthusiasts go to great lengths and through great contortions to try and cut these cans open, replace the lubricant, and seal them up successfully again. But there's nothing you can do with a broken integrated circuit. Either it works or it doesn't. And the compromise is often between exceptional reliability when a product is young and nightmarish maintainability when it gets old if there isn't a good supply of spare parts. And of course, the right choice depends very much on the application and the customer. So what we have here is a device which is much more specialized than earlier products and much more complex, both in terms of the number of components and the number of materials. And the parts come from all around the world. The Geiger-Müller tube comes from Holland, the capacitors from England and from Germany, and the new batteries, they come from China. And yet, this is still a product which is very nicely repairable. Now, I'm not going to tell you that everything was better 50 or 100 years ago. That's not true. When it comes to older products, there's always a filtering effect at work. The poorer products of the past broke and got thrown away. So we're left looking at the best of the best. And digital technologies have brought many new capabilities when it comes to repair. There are now machines that can diagnose their own faults and give the user an error message telling them which component to check. And with industrial control, much of the customization is now contained in the software. So if the controller breaks, you can just buy another standard controller and load your software onto it to customize it. And with the advent of 3D printing, if you can draw a spare part, you can make it. Of course, you wouldn't be watching this film without computers and the internet. But there have also been many backward steps. If you think of an electric kettle, it's now common that the heating element is permanently crimped onto the bottom of the jug so that it can't be unscrewed and replaced like the elements of the past. And I was recently looking at a computer monitor for a friend and found that to get inside, you had to take a credit card and push it through a cooling slot to undo a catch. Now, most people wouldn't have any patience with that. They would throw the monitor away. And it would be far better just to use standard screws and make these part of the design. Now today, we do have much better knowledge and understanding when it comes to design for repair. And this is why my key message is that we can do better. We can find a better compromise.